The first speaker is Dr. Albert Alexander. Let me introduce his short biography. Dr. Albert Alexander is a professor at Bangalore Institute of Technology, VIT. It is one of the top schools in India. He is the recipient of prestigious Raman Research Fellowship from the University Grant Commission, and he was a postdoc researcher from Northeastern University, Boston, America. His current research focused on fault diagnostic systems for solar energy conversion system and the smart grid. So today, he's going to give a talk entitled Applications of Machine Learning Techniques for the Performance Improvement in Power Electronics. So let's welcome Dr. Albert Alexander.
Okay, thank you so much. Thank you so much for this invitation. Am I audible?
Yes, please continue.
Okay, thank you so much. Thank you so much. Okay, so first of all, my greetings, my wishes to each and every one of you, okay, from the organizers, Professor Guanjin for inviting me, and Professor Dingley for inviting me as a first keynote for this conference. So it's a great gesture in sharing the knowledge and our expertise to the budding engineers. Thank you so much for this great opportunity given. So today my keynote is on applications of machine learning techniques for the performance improvement in power electronics and drives. So myself, we are doing some work in the area of power electronics and drives and how these machine learning plays a vital role. Because we do want this machine learning to be one of the case or one of the very important parameter, such a way that how this machine learning can be a very important task. To analyze this particular thing, okay, so my presentation overcomes this one. So these are some of the books which I have written on the area of power electronics, especially for electrical vehicles and also for solar photovoltaic systems and also the computational systems related to power electronics. Okay, so the interested peoples on this area can able to refer these books. When we talk about on power electronics is one of the very emerging branch in engineering, so which helps us to achieve the automation, which helps to provide the smart city, and which helps to achieve all our technological issues. Okay, so to overcome the technological issues. So power electronics can be defined as electronics for electrical conversion, where we normally use the electronics for the electrical conversion. So the power electronics applications are termed as CCC. First one is for conversion, where this power electronics is useful for converting from AC to DC or DC to AC or vice versa, like DC to DC or AC to AC. And this power electronics can also be demonstrated much well for control. So here our topic is completely based on this control. How this power electronics can be useful for controlling the appliances, controlling the electrical machines and control. And the last one is called conditioning. So these two objectives we are going to discuss in the today keynote. Let us talk about on this intelligent systems. Now it is going to be a very buzzword across the globe on machine learning. Okay, everybody talks about on machine learning. Okay, that means what is meant by learning. Okay, learning is defined as a very important thing that is called tuning. Okay, if I want to tune a parameter, that is called learning. So here what I will do, I'm going to make use of machine learning. So in this machine learning, I want to tune the parameters. Okay, even if we want to learn a new subject, even we want to understand a new concept, we have to tune ourselves. That tuning only we normally give by the word called learning. So learning is defined as tuning. How the learning process takes place in the machine learning phenomena. So here in the machine learning, we symbolically inspire with a biological thing. So when we talk about on the nervous system, okay, we talk about on the neuron structure. So in this neuron structure, whatever the thinkings which you are taking inside to the neuron, it will taken by your dendrites and it will make your inputs over there to the nucleus. But in between to the dendrites and the nucleus, there comes a gap. There comes a gap. That gap we normally call it as a synaptic gap, okay, which is already denoted by the term called, which we normally call it as a action potential. If you want to do any kind of task like running, walking, speaking, dancing, playing, whatever it may be, any task will be accomplished only by the tuning of synapses. So that tuning will be takes place biologically in our neuron. Even if you want to attend the keynote lecture, so the desire to attend or just to sit, it all depending upon how you're tuning your synapses. So whatever the inputs you are taking inside to your nervous system, it will be amplified or it will be projected with help of the synapses. And then only it will takes to the nucleus. Most of the contents, what we study, most of the contents, what we remember, it fails to reach the nucleus. That is the reason most of the contents are standing only with the dendrites. It know where it's going to the nucleus. So a machine learning is defined as a tuning. Similarly, in the biological inspiration, if you want to do any task, we have to tune our synapses. Then we can able to achieve anything. So this is the thing, how the neuron functions. Basically, the functioning of the neuron. Okay, so whenever we think anything, whenever we do any task, or whenever we want to do something, that is each and every task is blinked over here. The signals will be taken inside and it will be taken to the center part of your nucleus. Okay, so in order to take the center part of the nucleus, I want to tune this particular synapses. That we normally call it by the term called weights in the engineering concepts. Okay, whenever we want to do that, we usually say that I want to update the weights. So based upon this, okay, one practical application of a machine learning will be like this. I'm giving some set of images of a dog. I'm going to give the set of images as a cat. As a human being, we can able to easily recognize which is dog and which is cat. But I want to model a system. I want to model a machine learning such a way that, it has to predict or it has to detect that whether the image, whatever I've given is dog or cat. Okay. For an example, if I'm giving this particular image, so this image will be taken as an input. Okay. And it is giving us, showing the output as whether, so what are the features we can able to take from the dog? From the dog, I can able to take the features as the eyes. Okay, I can able to take the features as my ears. I can able to see the features as his mouth. Okay, that is, it's something different than that of a cat. Okay, so that we normally call it as a feature extraction. For an example, if you want to work with any kind of engineering problems, okay, even for powertronics or drives are concerned, the first and foremost prerequisite is we want to provide a set of data set. Once you have the data set in your hand, your work is nearly 99.9% over in your work. Okay, 99.9% is over, provided if you have a data set in your hand. The rest of the work is just a 0.1%. Okay, so that is, the data set is very essential when we work for the machine learning. I will be explaining with some kind of case study in which we adopted the machine learning to improve the performance in the powertronics in the forthcoming slides. So here I've given you the general example, such a way that if you want to predict which is the dog or a cat, I want to give the data set to my model. So this data set should be a reliable data set. This data set should be a benchmark such a way that my model has to provide an appropriate decision. That is called machine learning. So here some applications of machine learning will be is non-measurable. That is, it starts from infant to a young adult, from birth of artificial intelligence, and for the current state, it is moving across in each and every stages. So many people will be saying that this emergence of artificial intelligence and machine learning, which will degrade the number of employees in an organization. No, it will never reduce the organization, because we know that, this machine learning, we want to improve the reliability of machine learning. We want to improve the accuracy of artificial intelligence. In order to achieve that, we need more number of professionals who work in the area of AI and ML, machine learning, in order to improve the performance of your systems. Now, let us see what is meant by machine learning. as it is defined by Arthur Samuel in 1959. So it is a field of study. So machine learning is only a field of study. We call this machine learning is only a simple concept as a tool. It is only a tool. Okay. So we can say that, it is only a tool. Okay. So we can able to make use of this tool. Okay. So where it does not require explicit programming. Okay. So in the 1959, he has given this definition. So he wrote some checkers playing program, and he has made that particular program to play nearly 10,000 games by itself. So whenever we are playing any board game, okay, some of the games we will win, some of the games we will lose. Okay. So we will get us a good and bad. So while you're playing more number of games, okay, you will learn. Okay. You will learn by experience. Okay. And the task is to win the game, and the performance is how you are going to improve the performance from one after the other. Okay, so the first game you can able to learn the nook and corners of the game, how to win that particular game. So a machine learning can be established by experience and the task and the performance, ETP. So the experience is gained by number of programs or number of data set or number of works what you've done in that particular area, which makes you to experience. Whether experience alone is enough? No, you have to accomplish a task. Okay. So task is alone enough? No, you have to make some performance measure. So that task, you will getting some national recognition, international recognition. That is called the proper way of learning. So the learning can be established by the way of experience, the way of task, and the way of your performance measure. And what is the life cycle of machine learning? Okay. So here we can able to see that the task of machine learning is very simple. That is up to the life cycle number 1 to 4. Okay. Up to this 1 to 4, we talk only about data. We will collecting the data. We'll prepare the data, you clean the data, you analyze the data. So this is called the very important data science. So as I already mentioned you, once the data is ready in your hand, your work is 99.9% over. Okay, so here comes a question, sir, where I will collect the data? What are the methods are available to collect the data? You mentioned that while you're getting the data, your work is over in a day. Okay, because that means you imagine that how many papers we can publish, how many journals we can able to submit. Okay, because your data set is available in your hand, you apply some multiple algorithms. Okay, and then based upon the algorithms, you can able to publish n number of papers. Every year we set a benchmark of publishing not one paper or two paper. We set a target of publishing more number of papers. That should be the target for more number of researchers who are gathered over here in this particular forum. That is, we are gathering some kind of data. You apply some more number of algorithms. If you are not satisfied with those algorithms, you develop an algorithm. So that is the reason machine learning is also called as model-free learning. Model-free learning means that is, it does not require a general procedure. It does not mean that you have to follow the procedure that has been formulated by others. It does not mean that you should follow the same procedure what has been done by the previous researchers. No, you develop your own path. You even keep your name for your algorithm. That is the concept. So data set is ready. And here comes what are the methods are available to gather the data. I will explain in the case study. Once your data is available, you are going to develop the model and test the model. The two parameters we want to test. One is for its reliability, one is for its precision, one is for its accuracy. Okay, we want to make the model to be accuracy. The people will say that what is the accuracy of your machine learning model? Okay, how we have to check the accuracy. That is, if I want to predict something, you have created a model for the fault tolerant system. How many faults it predicts correctly? For an example, in the 100 samples, 50 samples it predicts correctly, 50 samples it predicts incorrectly, means your model is just 50% accurate. And then precision, how precisely it gives the results. And reliable, whether this model I can able to adopt in a driverless car. For an example, in a driverless car, I'm going to keep on AI. Okay, whether I can able to reliably sit in the driverless car, whether it can able to go, whether I can able to believe that what that speaks the reliability. And final stage only it is comes under the deployment. I want to deploy my work. So these are the various classifications of machine learning. So as according to our power electronics and power systems are concerned, we normally go for the supervised kind of learning, which can be classified into regression and classification. And unsupervised, we talk about on clustering. So when we talk about on this regression, as according to electricity is concerned, you can able to forecast the electrical load forecasting with the regression algorithm. Okay, for an example, in the 2023, okay, what is the power capacity in your country? Okay, and what is the power requirement in 2050? You can able to predict with the machine learning. So this machine learning will help us to make a prediction. That means, how can you define the machine learning? Making use of your present data, making use of your past data. So these two things are available. Okay, your present data is available, past data is available. Making use of these two things, you are going to predict the future. You are going to predict the future. That is called machine learning. In a very simple definition, I'm saying you know about your present data, you know about your past data, making use of your present and past to predict your future. Even for a fun, I usually say to my students that, you know about your present health data, you know about your past health data, making use of your present health data and past health data, you can able to predict the future of your health. That means you can even predict when you will die. When you will die, that also you can able to predict. I'm telling us a fun. Even we can, one day it will even come as a reality in the machine learning area is concerned. Okay. And here comes the process available in the machine learning. The first step is I'm going to collect the data. I want to process the data. I want to extract the futures. Finally, I can make use for the predictions. So the overall step is only on the data is concerned. Similarly, when we come up to the workflow of the machine learning, I'm going to take the environmental data. You can able to adopt any kind of algorithms. Okay. There are various algorithms are available in machine learning, auto-regressive models, support vector machines, random forest, probabilistic model, artificial neural networks. So these are one of the algorithms in the machine learning. So using that, you can able to go for prediction or decision making, classification or prediction or forecasting, whatever it may be, we can able to adopt with. So with the help of machine learning, we can able to achieve some key plots, visualize the data. For an example, if you want to predict the power capacity of China into 2050 or 2070, means we can able to visualize in the form of graph. Even your health data, you can able to visualize in your graph. Okay, how your BMI is increasing or decreasing. What is your current BMI? Depending upon your age and depending upon your weight and depending upon your height, you can able to predict what is your BMI. If you're using the same kind of algorithm, even you can able to predict that what will be your BMI for the next few years. Okay, so that is the visualization using the machine learning. Now, we understood, I have given you the inputs about what is meant by learning, what is meant by machine learning. Now, I'm going to explain you how we are going to apply for the performance improvement in the power electronics and drives. So here, we normally work with the grid interconnected solar photovoltaic systems. For that, we work with the control of inverters, maintenance of the overall system, cyber security using machine learning for the for making sure that whether the data is appropriate, there is no leakage of data. And this is very important thing on forecasting for our country and forecasting the power requirement for a country for the increase in population and for designing purpose. What is the optimized designing of the PV sizing like that? For all this is only a sample of the works. There are n number of works and unlimited works are available in applying the machine learning concepts, especially for the power electronics and drives. Now let us move on to the learning algorithms. Okay, so I'm going to tell you what are the different types of algorithms are available initially. Then I will explain you how we adopted those algorithms. So in this keynote address, my objective is I'm going to give some practical advice that what are the algorithms you can able to apply and how to apply them, and what are the tools are available to apply those algorithms. Now let us say one thing about the supervised learning. Okay, for an example, you want to predict the price of a house. Okay, for an example, you are having the X data is there and Y data is there. Okay. So X data will show you that what is the feet, okay, the size in feet of the house which you are interested to purchase or buy. Okay. And the Y-axis, it will give you the price in dollars. Okay. What is the price? So based upon the different hypotheses, what is the hypothesis means? One person will come and tell you that for 500 feet, the price is around $750. Okay. Some person will say that for 750 feet, you have to pay 1,500 into $1,000 like that. So whatever the things they are giving, the statements given by the respected sellers, they are called as an individual hypothesis. So you can able to, from this particular graph, you can able to understand for the 750 square feet, what is the money you are going to expect. So here in this particular graph, whenever I'm drawing a straight line, I can able to predict the house, maybe like $150 for this particular 500 square feet. For an example, instead of straight line, I'm going to draw a second order polynomial expression means it can able to go across around 2000 into $1,000. So I'm having a confusion that whether I want to choose a straight line or whether I want to choose a second order polynomial curved line. Because if you use a straight line, you will be the winner. If you're using a curved line, you are a loser. You are losing more money. So here comes what is the right answer. To overcome this, we are using a model. That model is called regression model. So this regression model will avoid the confusion that whether you want to choose a straight line or a curved line. That is called regression problem. So what is meant by regression problem? Because you know what is your feet, that is called X. You know what is called as your Y, that is your price in dollars. This is the size in feet. So based upon that, we can able to draw the regression line. Okay, and based upon your values, you can able to plot. Okay, and you can able to figure out what is the exact price of the feet. What is the exact price of the house you are going to buy? Okay, and we can also provide you a known real discrete linearization. And again, this is one of the problem we called as a regression problem. If you want to classify the disease like a brain tumor, if you want to classify, we call it as a classification problem. And then if you want to make sure that, that these are some of the problems which we normally call it as a supervised. When you go for the unsupervised problem, the unsupervised learning, this unsupervised is also called as unlabeled data. You don't have any target over here. But what you will do, based upon the inputs, you are going to make it as a groups. That groups we normally call as a clustering. So some of the examples of the clustering algorithms are when we talk about on the Google News, okay, we talk about on the genomics, and even we talk about on the genetics, microarray of genetics. That is, we are grouping as according to its different behavior or different characteristics, we are grouping into different things. So the machine learning algorithms can be classified as classification, clustering, or even a regression models. So when we talk about on the classification, you're going to classify whether it is yes or no, whether it is, you are going to classify the system, whether it is a yes or no. Okay. So for an example, one such classification problem we normally given by support reclamations. That's also classification algorithm. When we talk about the regression, you know about X, you know about Y. Making use of X and Y, you draw the line. Okay, so that is based upon your present data, based upon the past data, based upon the X and Y, you are drawing the line. Based upon the future, you are plotting this particular thing, and you can able to see how much it deviates from your basic line. That's called regression. And even when we talk about on the classification, there are so many algorithms on classification. So one is called, so we know that, this is called as a linear regression, where you draw the line linearly. Logistic regression means, so that is, we can able to see the regression will be like this. That's called logistic regression. There is one more regression will be there. That is called locally weighted regression, where you can able to make the points to be like this. And one algorithm is called support vector machines. That is useful for the classification. Let us say that I'm going to classify into this and this. Okay. So here, while classifying, I'm making use of these data sets as a vectors. These data set as a vectors. Okay. These vectors will be supporting me in order to classify. That is the reason this algorithm is called as a support vector machines. What is called as a vector? A vector is the points that has been available. So applying the algorithm and implementing the algorithm is just a half a day work, or even we take about it's a 1 hour work. You can write so many papers for the works what you have run. Even you can write with there are different types of support vector machines also available. Kernel support vector machines, naive basis, decision tree, random forest. For each and every algorithm, you take one algorithm and then publish the papers. And you compare the algorithms for your data set, for your problem, and publish a paper. So publishing a paper in machine learning for this application is keep on increasing day by day. Over a period of time, this also will become obsolete. We will go for other kind of new technology. So when the technology is alive, it's very essential for each and every one to publish more number of papers. When we talk about on instance-based learning, this is one of the type of learning. So it has been classified as self-organizing map, learning with the quantization, locally weighted learning, case-based learning, and k-nearest neighborhood. So these are the different types of learning methods. I'm just making what are the learning methods which I have done, what are the algorithms which I have worked with. So for my general problem, I can able to apply this algorithm when it is unsupervised, when it is called as supervised. Okay, most of the applications of power electronics and drives, we normally apply this back propagation. It comes under the supervised learning, under the feed forward nets. So we will be applying all these algorithms to make a classification. So now we come across to the general problem statement for power electronics and drives. So let us say that why we require this machine learning or the artificial intelligence. So let us say that if you want to go for a speed control application, you are going to set the speed as 1500. Okay. So your controller is set as 1500. This is your target to set the 1500. But you will never achieve 1500 initially. So what the controller will do, it will go for some delay time. It goes for the rise time, it goes for the maximum peak, and then it will comes to the settle, and then it comes to one particular thing and reaches your target. So the time taken from 0 to reaches to the target, this is called the time taken by your controller to achieve the task. You can work with any kind of controller, but we always concern about the time taken to accomplish your task. Some controllers, it will take more time. Some controllers, it will take very limited time. So the time plays a very important role in achieving your task. So this time, we normally call it as a computational complexity. They will ask the question about that. What is the computational complexity? It means then how much of time it is taken by your controller to accomplish the task. So this is one of the application what we discussing for the drives, So this is your input power. We are using a DC to DC converter, and let us take about that where we are using a motor. Okay. So this is you consider this as a motor load, and this is you are taking the actual speed of the actual voltage. You're giving the reference voltage. This is going to be the comparator. So the comparator will give you the error signal. So the overall objective of the machine learning and artificial intelligence is only the compensator, or it is a tuning parameter. Why? To overcome the error, which we normally call it as a controller. Okay, what is called as a controller? The only role of the controller is to overcome the error. Once it overcome the error, it will give the signal, which signal we normally call it as a control signal, or we normally call it as a modulating signal. That modulating signal will be given to the pulse width modulator, and that has been given to the gating pulse of your switch. That is called the role of the controller. So the rest of the things, it has already been available. That is your power source, converter, motor load, and the sensors, comparators, and the PWM, everything is available. So our task is making this particular control part to be much more intelligent one. So now I'm going to explain you with one small case study for the next 5 minutes. Okay. So here we have taken around 5 solar panels. 5 solar panels, and we have given to the inverter, power electronic inverter, and we have given to the AC load. Okay. So here we saw the problem statement is we have fixed the alpha values or the switching sequence for the inverter. When we fix the switching sequence for the inverter, we found that the output is quite distorted, and also the harmonics percentage is also very high. So to overcome that, we are going to make the alterations for the alpha values, the switching angles. So we want to create the data set. So the data set is created based upon the Fourier series expression. So we know the output voltage. We know what's the panel voltage, the 5 panel voltages. So we are setting the inputs as a panel voltages, we are setting the output as the alpha. So based upon this, we have derived the expression for the harmonic elimination expression. That's what I already mentioned you. There are various methods are available to acquire the data set. One is with the help of simulation. One is with the help of doing experimental studies. One is with the help of doing the mathematical modeling. And one is with the help of the formulas, what I'm showing now. And one is by making use of your repository for calculating the data set. Or you can able to download from any Kaggle or whatever it may be. But you also want to make sure that the data set, whatever you are taking, you have to cook up the data set. Here we cook the data set. And finally, we arrive the sample data set like this. That is for the different variation of the panel voltages, what is the corresponding alpha values. Here we are using the 5 inverters and what are the alpha values for the 5 inverters. So for the variation of my panel voltages. And this is what the trained neural network. So we know that, so for the input, I'm giving the panel voltages, 1 to 5 panel voltages, and it will provide you the 5 alpha values. And this 5 alpha values will be compared with my triangular carrier, and it will produce my switching pulses for my inverter. So the neural network will never produce the switching pulses. It will give only the modulating signal. This modulating signal we have to compare with your triangle waveform in order to generate the pulse. Now these pulses will be given to the inverter to get the appropriate waveform. This is a 11 level output voltage waveform based upon the variation of solar panel voltage. And we analyzed with the conventional PWM method, we found that the THD is quite very high, and also the amplitude is about the individual harmonic orders is also 5 and 10 like that. So more number of things. Even the third order harmonic, it reaches up to magnitude of 30% of the fundamental. So with the help of this neural networks, that is with the help of ANN, we got this THD of 7.92. We can able to see that the magnitude is only about 3 and 2. It does not reach us more than 10 or like that. So we are not satisfied with this THD because it was not as per the IEEE standard. So we made one more work with a 15 level inverter. So we have taken even the floating point numbers as an input data set, and based upon that, we have calculated the switching angles, and we have designed this real-time implementation. We have implemented with 7 inverters, 1, 2, 3, 4, 5, 6, 7 inverters with the 7 input solar panels and corresponding to the load to achieve the 15 level. So we have taken the variations in the input. Okay. So that's what I already shown you the sample data set. So 7 panel voltages, 7 alpha values in the radians. So this is the architecture what we have done with the 7 inputs and the 7 outputs. Okay, we have done with the 2 hidden layer with the 20 neurons, the first hidden, second hidden of the 10, and what are the. This is the algorithm we have implemented, Levenberg-Marquardt algorithm. This is the advanced backpropagation algorithm. And then we have, for the comparative purpose, we have taken for the 11 level, the THD is 7.92. For the 15 level, it is about 5.69. You can also see the magnitude of the harmonics are less than 1%. Okay, that was our achievement. Okay, so this is what the thing we have obtained for the results for the inverter, which we have developed with the help of this machine learning technique. And we also wanted to implement the same in the hardware. So we have it was funded by government. So we have taken the inputs of the 7 inputs and we have given for the 7 inverters, and the programming has been made, and the variation of the alpha has been taken with our software, and this has been the power quality analyzer, which will keep on monitoring that variations in my output. So this is the switching sequence of the alpha values for the different variations as per my training variations. And this is the overall experimental setup which we have developed. And this is the hardware results what we obtained for the 15 level, and corresponding what is the harmonic elimination we obtained. So which has produced the harmonics RMS value of 230 volt and the 50 hertz of frequency. And what are the harmonic magnitude of the individual orders. Okay, we have taken up to 20 orders. So at the end of my talk, okay, I can able to give one indication that the take-home message of today. So today we have discussed about on the keynote on how to apply the machine learning for performance improvement in the power electronics and drives, and how to figure out the problem. So today take-home message will be there is a more availability of renewable energy sources. We have to make it and make use of it appropriately. And there are so many unaddressed problems in the machine learning and the deep learning and also the power electronics. So we have to address all these problems, and there are so many scope is available in this related area. So we have to make towards a smart grid, microgrid, and distribution grid. Everything is much more moving towards a smarter, and we are going to work in the highest role of interdisciplinary by involving the electrical engineering with machine learning. Okay. So with this take-home message, I just ask any questions. Okay. I conclude my talk after this. And I wish to thank each and every one of you, okay, for giving me this great opportunity, okay, for taking this keynote address in front of this August gathering. Okay, thank you so much. Okay, so thank you so much. Thank you.
Thanks, Professor Alexander. Thanks, Professor Alexander. He gave a talk about the applications of machine learning, especially he talked about logistic regression, KNN, support vector machine, live Bayes, and the decision tree, random forest, and the unsupervised learning. And he gave an insight how we can improve the power electricity performance by using machine learning. So if some of you are interested in his topic, because he published several books and articles, so please feel free to contact him and get advice. So once again, thank you very much, Dr. Albert Alexander.
Thank you so much, sir. Thank you so much. Thank you. Thank you all. Thank you all.
Yeah, bye-bye.
Thank you once again. Bye-bye, sir. Thank you.
Okay. Next speaker is Professor Christian Martin. Dr. Christian Martin is an assistant professor at University of Malaga, Spain, and a researcher at the Etris Research Group. Previously, he received a master, two masters, and one PhD in computer science from the University of Malaga in 2014, 2015, and 2018, respectively. He has worked as a software engineer in various tech companies with RFID technology and software development. So today, he's giving a talk entitled Connecting the Data Stream with Machine Learning Artificial Intelligence Frameworks. So welcome, Dr. Christian.
Thank you, everyone. Can you hear me?
Yes, we
Can you hear me?
Yeah, hear you.
Okay. Thank you. Can you see my screen?
Yeah, we can see your screen.
Okay, thank you. Thank you, Professor Wangir, for your introduction, and thank you everyone for inviting me for this talk. It's a pleasure to me to be part here of this conference, so thank you everyone. Today, I think that before we were discussing about machine learning, so I will continue discussing about machine learning, but with a different approach, because we are right now in the area of streaming data and real-time data, and normally the framework that we are using with this streaming data, they are not prepared to work with the streaming data. So the work that I'm going to present today, KafkaML, try to fill the gap between the streaming data and the machine learning framework. Okay, the title of the work is KafkaML, connecting the data stream with machine learning and artificial intelligence framework. I pretty like this picture because you can see an overview of the IoT in a smart city, for example. The IoT is of course involucrated in the cities with real-time parking, also to monitor breaches. We developed some projects to do structural health monitoring for the critical infrastructure like breaches, also for nuclear power plant, connected car, etc. So the IoT is almost everywhere, and right now is getting more devices connected. This is a prediction that right now we are almost 14 billion of devices connected, but for 2025 it will be more than 27 connected devices in areas and wireless technology like 5G, LoRa, so on, that for sure you will know. So we are getting a lot of device, a lot of data, and of course we have to use this data, because if we don't take some insight for this data and some knowledge, we will get nothing. So we are getting a lot of device, a lot of data, so that's why where the machine learning artificial intelligence play a key role. So right now we have this situation. Probably this is two of the major framework right now. For example, TensorFlow is one of the framework to do machine learning, one of the most famous. And right now, Python also is very famous. I think that if you had done something about machine learning, maybe you have used some of those. Okay, the situation right now is that they are prepared to work with data storage or data set or file system, okay? But they are not prepared to work with data stream. So we do have a problem here, like you see, like, because we are connecting a lot of devices to the network. We are receiving a lot of data, but our main framework in the community, they are not prepared to work with that. So we will need a solution for this problem to take advantage from all the data that we receive from the IoT side. And we can have this problem before. For example, imagine that you want to get some data from IoT device, okay? So you have here some IoT device on the left, some temperature. You could also have some mobile phone, some Arduino, or maybe some smart gateway. So maybe you create a solution to send all this data to one machine learning solution. For example, Apache Spark. But in the big data field, you don't trust only in one solution, because every solution has one specialty for one type of processing. So maybe you, a part of Apache Kafka, you use another one, sample. But the problem is here, when you have many solutions. So you have a problem of integration in this scenario with a lot of consumer, a lot of producer, and a lot of consumer, okay? So we have kind of this problem in the past, and we use Apache Kafka because it's one of the best technology right now in the big data file to connect and to integrate a lot of producer and a lot of consumer. But beyond integration, producer and consumer, we have a lack of a standard by deploying a machine learning or a deep learning model. For example, you can do your own integration based on Flash or create an ad hoc application. You could also use TorShare or K-Share or TensorFlow serving, fast API. So what is the problem here? We do have many technologies to deploy a machine learning model. We need some kind of a standard in this sense. Moreover, when you are going to deploy a machine learning model or a deep model, normally everyone focus on the machine learning code that we have here. But if you see the big picture like this, the machine learning code is only a small piece of the infrastructure, because we need a serving infrastructure like we saw before with the solution that we have right now in the field. We do need also some monitoring techniques to monitor how our solution, also data collection, some configuration for our model, feature extraction, machine learning resource management, and so on. So just to keep in mind that when you are going to deploy a end-to-end machine learning solution, just the code is only a small piece of our setting. So with this context, we came up with KafkaML. We have the problem of data string that they are not prepared to work with machine learning solution. Also, the lack of standard to deploy the model. And finally, we have to provide a complete solution to deploy our model that we saw before. A serving infrastructure, monitoring, configuration to easily deploy the model for final user. So this is our framework, okay? KafkaML. KafkaML is basically an open source framework that essentially integrate the data string and machine learning model and manage the life cycle of machine learning and artificial intelligence application. So this is an open source framework. You can see here at the title, the GitHub repository. You can check out all the source code are there. So you are more than free and more than welcome to test it and evaluate. Also, here at the bottom, you can find the publication. Okay, so I'm going to explain a little bit about the pipeline that we can have with KafkaML. The first thing, of course, is to define a model. You can easily define a machine learning model in the web platform with very little of code. When you have the model, you can create a configuration. Basically, a configuration is a set of models that you want a group to deploy together and to train different models in parallel. Then you have your model, and you deploy the model for training. And don't forget, we are using data stream. So in our framework, we are ingesting data stream data through Kafka to our deployed model in our infrastructure. So you have your model, they are trained, so you can deploy for inference. You can deploy your model to get prediction in real time. And of course, again, we are with streaming data. You can send streaming data through Kafka to get real-time prediction. So this is an overview of the pipeline. As you can see, from the beginning until the end, all the data that we interact with our model in terms of training or inference is everything about streaming data. This is an overview of the architecture, okay? Kafka is designed to be deployed in a Kubernetes infrastructure. So every component, for example, a machine learning model that it will be deployed, or an inference model that will deploy to make prediction, a part of the backend, the front end, the Kafka itself, everything is deployed in a container in the infrastructure. So with the container, we can control things like replication, fault tolerance, everything. And also our infrastructure is open for possible station in the future, because we have a microservice infrastructure, so you can easily add more components and control this life cycle, okay? So this is a small video of the Kafka ML platform, okay? You can see here some of the deployed model that we can have in the platform, okay? You can see here some metrics, the training time, the validation, and accuracy. So when you have one model, you can check the result. For example, you can see here the confusion matrix of one model, and also you can check out the loss and accuracy of this model very easily and very user-friendly, like you can see. You can also download the metric and check out the confusion matrix, okay? This is after training. And when you have the model, you can deploy, you can get the training model, and it will download a model like this in S5 format. And also you can deploy the model with inference. You can configure some replicas and the one top in Kafka, and you have your model ready for inference and to make application, okay? So you saw overview of our platform, and I'm gonna ask some questions. For example, can I reuse the same data stream for different models? Even after a long time? Can the model be trained in parallel? Imagine that you have different machine learning models and you have only one source of data stream. You can reuse this data stream pipeline to different models in parallel. And you know the GPU power. Can Kafka ML adapt itself to infrastructure with GPU and no GPU support? So the question to all these answers are yes. You can do that with Kafka ML platform, and like I said before, it's open source. So beyond the model, you can have a fine control of the data stream that you have in Kafka ML. So let's make an example. For example, you send some data string to the Kafka ML platform. When you send some data string, this is the data string. And when we send a data string in Kafka ML, we send an control message to indicate the data string that we have, okay? So this message basically indicates the beginning and end of the data string, some property, and so on. So this is one data string, and maybe in the future we send another one. So we have right now in Kafka ML 2 data streams, okay? The blue one and the orange one. So imagine that in the future you want to reuse this data string, the blue one. So this data string is in Kafka because Kafka doesn't delete the message. You can control how long the message can be in the queue. So since we have the property of our message, we can do that. We can only send a control message to our new model in the future and reuse this data string pipeline. So we can have a fine control of the data that we have in our platform. Just sending a few bytes of control message, we can reuse all the data that we have in Apache Kafka very easily. Of course, this is one message that hasn't finished yet, so we don't have the control message, but when it's done, we will receive the control message to use in the future. And one problem that you may have also when you are deploying and you are evaluating machine learning model or a deep learning model is to provide some result to your client and to visualize your data. So in this case, you have different options. Maybe you train your model and you have everything ready and you wanna see how the model behave with real-time data, or maybe show the result with to your client or to every customer, okay? So with Kafka ML, you can easily do fast prototyping of machine learning application. That is one part of Kafka ML where once your model is trained, you can easily deploy your model to visualize your data, for example, a monitoring model. Here you can see overview. This is overview for the famous means data set where you have, I think every you know, you have 10 labels from 0 to 9. So you can easily see here the histogram of all the prediction. And this is the real one, the last one, the last prediction. So the last prediction for the means data set was 1. And this is also a history of the prediction. 4, 9, 4, 4. Okay, so you only need to configure some label, and this color also are configurable in Kafka ML. So this orange or this purple, this green, you can easily configure here at the beginning and some topic from Kafka, and you can easily check out your model very fast in our platform. So it's very powerful because you just need one model, just send data, and very easily you can visualize your model. For example, you can see here, this is from some of our projects. We deployed an IoT prototype in a natural park here in Spain. You can see here some water sensor that we deploy in our park. So they are monitoring the water pollution and so on. Especially they are monitoring the nitrate, because the nitrate is very difficult to measure in real time. Okay, because to measure the nitrate in real time, the sensors are very expensive. So with other kind of sensor, we were monitoring some water property, and with a machine learning model and doing regression, we extrapolate the nitrate estimation. And this is also the visualization in KafkaML. So we are sending data to our model, and we can see here the nitrate estimation. Okay, so beyond that, in KafkaML, you can also deploy distributed deep learning model, okay? I don't know if you are familiar with distributed machine learning model or not, but imagine that you have a big deep learning model and you want to split in piece. For example, one piece will go to a edge device and the other piece will go to the cloud. Why? Because maybe this deep learning model doesn't fit in your edge device because it's too big. So you want to split, and maybe you have an intermediary output layer in the edge, and maybe the rest of the model will be in the cloud, that you have more power in terms of computation. So maybe in the cloud, because you have everything on the layer, you can have a fine detection, but in the edge, you have some layer, not everything, but you can also do a early detection, especially for the case that you need very low latency. So this is some measure that we did in this use case. So we were deploying different model in different settings to evaluate the latency of this model. As you can see here, the latency in the edge is much lower than the latency in the cloud. That's why it's normal, because the edge is normally close to where the data is produced. That is the IoT. So the latency is much lower than in the cloud. And you can say, okay, but this model is not doesn't have that many layers that the whole model in the cloud. Maybe you can lose some accuracy. Yes, you can lose some accuracy, but as you can see, we have here 87 accuracy in the whole model, and in the model that we have in the edge, that is, like I say, a small piece of that, we lose some accuracy, but it's only from 87 to 82. Okay, so we lose that, but the time is almost the half. So for critical situation, we can have very low latency, and the accuracy is as much as good that we can have with the whole model. So this is the conclusion and future work that we are doing with our framework, okay? So KafkaML is, like I say, is a machine learning framework, open source, that you saw that everything you can use it, all the components, you are more than welcome to use it. You can use, for example, to deploy air monitoring application, whatever application you have to with real streaming data. Okay, you can also deploy a distributed deep learning model very easily, and from the KafkaML, I didn't mention also, but you can deploy the different pieces. For example, you can deploy the piece of the edge and the piece of the cloud in different settings, and just from the platform, okay? So you can deploy different distributed machine learning model, and also you can do fast prototyping of machine learning application. We were seeing before that you only have to configure a little bit of the label and the color and everything, and you can deploy your machine learning application and to show some fast result to your client with the platform. And at future work, we are doing incremental learning, okay, to always train the model when new data arrive. We are doing that, and we have one release version in the repository. We are also in the progress of doing federated learning. So the idea is that with data stream, we can also do some federated learning. And this is almost done. Federated learning and incremental learning is almost released. And we are also interested in future work to do dynamic distributed neural network partitioning according to different infrastructure, improve the thread changes of model evaluation. And right now we are also supporting TensorFlow and Python. So we would like to support new framework in the future to improve our framework. So that's all from my side. Thank you very much for inviting me to this seminar. And if you have any question, please just let me know.
Thanks, Professor Christian, for your valuable talk. So in this talk, Professor Christian, to connect the data stream with the machine learning AI framework, he created a new model platform, Kafka ML. So by using Kafka ML, this is a novel and open source framework that enables the management of machine learning AI pipelines through data streams. This Kafka ML is released on GitHub, so any of you can access GitHub and download. And you can feel free to contact him to get some more idea. And you also can refer publication, because in the below the presentation we could see IEEE access, future generation, the journal as well. So you can get some idea. Also, you can feel free to contact Dr. Christian. So thank you again for your valuable talk. Yeah.
Thank you everyone, and thank you for the invitation. Have a good seminar and conference, everyone.
You ready?
Yeah, almost.
Okay. Please tell me once you are ready.
Yes. First of all, thanks for inviting me to this conference. It's a pleasure for me to be within this panel of amazing keynotes. So thanks for having this, making this possible. I'm just opening my presentation.
Okay,
Just
so
a second.
while he's opening the presentation, let me shortly introduce his biography. So Professor Marco Anicetti is a full professor at the University of Milan. His research interest in the area of computational intelligence and its application to the design and the evaluation of complex streams and services. He has been investigating innovative solutions in the area of cloud and web service security assurance, evaluation, and software service certification, where the computational intelligence provides new notions of ordering and matching of security properties. So today, he's the last speaker, and he's going to give a talk entitled Handling Service QoS in Edge Cloud Continuum. So let's welcome Professor Marwan Hizipli.
Thank you very much. Can you see the presentation?
Yeah, please begin.
Okay, if you see the slides, I can start. So thanks for the introduction, and thanks again for inviting me to this conference. I would like to show you an example of cloud continuum architecture, which is a kind of advanced architecture that could host services, including computer vision ones, and their application in different contexts. Specifically, we are focused in the context of hospitals and health, and the relative services that could be offered by the hospitals to the patients or by the hospital to other hospitals in order to realize multi-centric study on the different pathologies. So what's the Edge Cloud Continuum? It's a kind of new paradigm where you have the possibility to distribute services across the connectivity established between the edge and the cloud, and also on the device. And this new paradigm is also coming with different peculiarities. First of all, the possibility to use different resources for computation, for instance, vast resource in terms of computation capabilities in the cloud, but also low latency using edge, and also being capable to deploy on premises some part of the service in order to comply with the different regulations in terms of privacy, for instance. So we can differentiate a set of requirements depending on where the services will be deployed and executed, and most of them are security and privacy related. So in case of on-premises, we may have the higher privacy applied, while in case of cloud, we need to rely on the cloud to keep the privacy facilities and to keep the privacy property. So the challenges are several. Let me just show the fourth that we have in our mind while we designed this solution that we call the Musa. Musa is a project, it's a European level project, and it's also the name of the platform that we are developing. First of all, we have a challenge based on the fact that when you want to release a service that is made of different components, then it's a composition of services. And making the composition of services working is quite challenging. So we may have a service capturing streams of videos. We may have a service doing some pre-processing on the video, like coding, etc. And we may have a service doing analysis on the videos in order to find specific pathologies or behavior that should be corrected by an intervention of some intervention of magicians or some experts in the area. Then so its composition of services could be complex to achieve. Then we have the need of maintaining some specific properties like privacy in the case of streaming videos containing information about patients and the pathologies, or even sending images for telemedicine or remote consultancy. Then this could be complex in the cloud edge continuum, and we have a lot of issues, especially in Europe, where we have a very strict regulation in terms of privacy. Then there are several places where you can put the service, not just in the cloud, but also in edge devices, but also nowadays in 5G edge devices that could be offered by the different providers of telco to the different clients. And then we have to consider that on these premises, we are not alone, in the sense that there may be a set of services that have to be composed together, and we need to handle this coexistence of different services on the same premises, because basically the service provider will offer the same facilities to a number of customers that should have the same service in place. Our solution is to address these 4 challenges by automatically decide how to compose. So it's no more a matter of leaving this composition to the programmer, but we can compose the service on the fly, and where to deploy. So decided where to put these services depending on the property that we want to keep. Then we may have different quality of services to be generated based on this deployment. Then we need to use this deployment to provide the continuum, and in order to build this continuum, we need to build the connectivities among the different premises. So from edge to cloud, and maybe from edge to far edge, like a 5G node, and from 5G node to the device. So we need to put the agents on top of these premises in order to set up this connectivity. And in order to guarantee the composition and the independence of the different services, our solution is based on containers that allows to containerize services and to execute them without the need of fully providing, for instance, a virtual machine. So this presentation, I would like to concentrate my attention in the part of related to deployment, while we keep the rest for, let's say, for that are almost achievable through literature in the list of related work that I have in the end of this presentation. So I will show you the deployment part. So the issue is how to deploy. So where to put services based on the property that we want to keep. So as soon as we want to keep some kind of properties, that we need to select the suitable location to put the services. For instance, if we need to have a specific performance, that edge computation could be not enough and we need to use cloud. If we need to have a low latency, that we need to move our service to the edge, very near to the data sources, in order to keep a low latency. And if we need to have a more complex properties like privacy, that we may need to put everything on premises in order not to move data. Or we need to put the on premises some kind of preliminary analysis like anonymization, etc., in order then to move the rest of the computation to the cloud or to the edge without any privacy issues. So the goal in this case is just to treat this set of issues in an automatic way. So and our let's say research main focus here is based on the notion of deployment, and specifically our claim is that based on where you decided to put the services, so based on deployment decision, you may have some quality of services or may not. So in this case, deployment is important. So imagine that we have this scenario, which is the Musa one. Again, Musa is the project that we are running in Università degli Studi di Milano. And we have 3 main entities: the cloud service provider offering services, telco providers offering the telco nodes and connectivities, and Musa clients that are the clients of the system. First of all, we have the client that want to deploy a simple, let me start with this simple scenario. They want to deploy this simple composition of services made of 3 services, S1, S2, S3, called in a row, so one after the other. And the client also express the need of some specific requirements, R1, R3, and R4 for the 3 different services. Now the service provider and the telco operator are capable to offering deployment facilities in order to cope with these requirements and to keep the connectivities up and running and allowing the execution of this composition of 3 services on the different premises. So we have S3 on premises in the client, then we have, so for instance, on the device, then we have 5G nodes hosting part of this service S2, and then we have cloud doing the service S1. So imagine that this is a kind of a video analysis application. Then we have the part related to acquisition on the device on premises, so S3. Then we have partially delegated the computation to the edge node, the near edge node on 5G network, like doing obfuscation of faces in order to prevent issues related to privacy. And then we have S1, which is receiving the videos without faces or anonymized in terms of faces, and then do analytics like trying to find behavior that are not allowed in that specific area, or aggression, or whatever we want, but without having the faces on it. So this is because we want to keep the privacy, for instance. So this is the scenario that we are trying to address. And our idea is to, starting from the initial declaration of the service that we want to merge together in order to build the composition, realizing this and executing on the cloud continuum as it is designed into this in this image. So we, in order to do this, we need to rely on the fact that each facility shows some kind of capabilities. So on premises, the capability is to keep the video private. On the 5G node, the capability is to do processing live. And on the cloud, the capability is to store the results and do advanced behavioral analytics requiring more computational capabilities than the one available in 5G edge nodes. So there are several works that trying to address the issue of deployment of services in different premises, but most of them are focused on finding optimal deployment in terms of computational capabilities and resources in general, while in our case we are focused in keeping advanced non-functional properties, not just performance and memory, but also privacy and security and confidentiality and all the other properties that are important in such type of environment. And there are also some very advanced and interesting approaches that are based on machine learning, like the reinforcement learning one, that could decide where to put based on a machine learning, so or based on a model deciding where to put that have learned from experience. So we do this state-of-the-art search, and we found that in most of the cases, the issues that are mostly important to address, and they are not that is not very addressed by the current literature, is the one related to the adaptability of the context, and the one related to the fact that this quality of service deployment should be driven by property and not just by computational capabilities, for instance. So let me go quickly into our methodology. So how we achieve this capability of deploying on the different premises based on the characteristic of the model to be deployed. First of all, we start by annotating the model. So as we did in the example, we have this sequence of 3 services annotated with 3 different requirements. So this is the annotation. This is done by the client that want to keep some specific non-functional properties for specific services. Then we need to annotate, we have annotated facilities by the cloud service provider, telling us which are the facilities that can support specific non-functional properties. So we have on one side annotation by the client, on the other side annotation by the service provider. So what we need to do is matching between requirements and what is offered by the cloud service provider in order to find the best match. And we also have this notion of capabilities, that is the capability of supporting specific requirements. But this is not enough. Having done this matching, we need to generate what is called deployment receipt. So it's a description on how to deploy these services in specific locations. So how to move the service and how to install and execute the services on top of that specific device. So it's like having files that could be moved and executed and installed everything that is needed in a specific location in order to execute that specific service. And this have to be done for all the services in the same composition at the same time, and without really installing anything, but just deploying the image in the Docker, so in a composed fashion. So when we have this receipt, then we can do the deployment and then execute. So what about the execution engine? So it's not just a methodology, we also have the execution engine, which is capable to receive from the client the request of building a composition of services and then designing this composition and executing it on the premises through the agents. So we need to put agents that is a kind of piece of software that is capable to then execute the receipt coming from our engine on the different premises. So we may have agents for the cloud, agents for telco edge node, and agents for on-premises, and they need to find hooks to connect to the facilities and to do the executions and the deployment. So these hooks are important and should be somehow exposed by the different facilities directly. So let me show you an example, and then we will move to the experimental evaluation. So first of all, we have this example, which is a little bit more complex than the prior one. We have 4 services in this case. They are similarly to the previous one, composed in a sequence. So S1, we'll call S2, we'll call it, and then call S3, and then call S4. So it's a sequence of services with the different requirements. So all the requirements are then moved as an annotation to the different services. So for instance, in this case, we have R1, which is confidentiality via isolation, so via containerization, basically. Then we have requirement 2, that is important for other services, that is integrity at rest, so keeping the final result untamperable. And then we have some constraints on the different connectivities. These constraints will have an important role in the decision of deployment, because we need them to be aware about the constraint and be capable to keep the constraint while deciding where to put the services. So we also have annotation on the deployment facilities in order to annotate the capabilities. And imagine that we have this set of 3 facilities, F1, F2, F3, that are basically cloud, edge, and on-premises. And for the 3, we have 3 different capabilities. C1 is capable to provide confidentiality. C2 is capable to provide integrity at rest, thanks to a service that is hosted on top of these premises, offering this capability to sign everything that is moved to the rest, so moved to the storage. And then we have the different constraint in terms of the bandwidth. So we have this graph, which is similar to the one related to the composition to be deployed, but is annotating the facility where to deploy. So the idea is to build this matching in an automatic way. And this is an example of matching. So imagine that we have the original 4 services with the different requirements, and then like R1 for S1 and R2 for S4. And then we have the capabilities on the other side. Our algorithm is capable to compute the matching. So this M1, M2, M3, and M4, saying where to put the different services on the facilities in order to be executed. In this example, we can see that S1 is moved to F1, that S4 is moved to S3, and then S2 and S3 will be placed on F2. So after this deployment decision, we will have all the services in the different locations, and we are aware and we are sure that they can be executed with the specific requirements that the clients want to be sure about. So to be satisfied for the specific execution of this specific service, which is made of a composition of 4, by the way. So after that, we have the matching, but we still need to build the receipt. Used in a composition. So I just put here an example of the composition in a facility F3, because it's the most complex one, since it requires to have an additional services in place in order to be then executed and to do the signature. So in this case, we have S1, SI. It is capable to sign instead of just saving. So thanks to this deployment receipt we can generate out of the matching, we are capable to execute this composition and to preserve the integrity property on facility F3. And this is an example made of with Kubernetes deployment receipt that is anyway again automatically generated out of the matching for all the facilities and all the services so that they can be put there and executed. So we did a kind of evaluation, a preliminary evaluation in terms of what we can expect out of this in terms of performance, because we need to match premises with requirements, and this is normally could be time consuming and could be a kind of exponential complexity in terms of the number of the services to be matched. But if we keep the number of services quite limited, as well as the number of facilities, that we can obtain some kind of interesting performance, even in this version, which is not optimized. So we have this exhaustive algorithm, which is not optimized, and in the future work, we will design an optimized one. So our idea is then to find an optimal solution via some kind of optimization algorithm that could lower this computational cost required to find the optimal deployment. So we applied this solution in the context of the Musa pilots, in specifically for modeling pathologies and for finding issues based on scans, like a scan coming from tomography or scans coming from other image system of the hospitals. And we want to do pre-processing on premises in order to keep the privacy, and then share the results among the different hospitals at the level of federated, like the kind of federated learning. And in this case, we are capable not to share any sensible data among the different hospitals. And this is executed on top of the Musa, anyway, the Musa platform. That we also have some pipelines that are related to analytics executions for chemistry and pharmacy. They want to execute a very costly computation to finding new molecula to be used then to improve the quality of some medical equipment or medical, let's say, device, or in general medicines. And this is high performance, so it requires computation mostly on the cloud. But the data could be have to be kept private for the fact that it includes a lot of intellectual properties for the chemistry industries and the pharmacists. And also we have a number of different applications that are based on telepresence and remote medical assistance that have to deal with devices like a mobile device, 5G nodes to keep the connectivity, and then cloud services that could do some kind of preliminary analytics analysis on the issues that a patient may have remotely, and then decide which are the suitable medical hospital to drive this request prior to contact the real medical and experts in the area. So, and this is my conclusion. We have this Musa platform, which is capable to realize and deploy complex composition of services, just describing them among a set of available services and adding to them the request in terms of quality of service, including performance and non-functional property. Then Musa is capable to do the rest. So realize the composition and then deploy the composition on the suitable premises and execute this composition instead for having trusted assurance about the fact that the properties are kept continuously working and up to date in that specific premises. So we have this applied this in a number of different scenarios, and we are keep applying this within the Musa project, and we are trying to find additional pilots that could be even international ones. So if you have any pilots that could be deployed in this continuum, even image processing, heavy image processing ones, please contact me, and we can maybe establish a kind of collaboration among us using the Musa platform to execute your own analytics pilots. So thank you very much. This is a set of references, and thanks. If you have any question, I'm here.
Thanks, Dr.
I cannot. Yeah.
Yeah, thanks,
Thank
Dr.
you.
JP. So in this talk, he gave a presentation on autonomous quality of service-aware deployment solution for edge cloud, and he also compares the QoS request with the capability of a given continuum in order to find, generate, and execute a solution suitable deployment. As you are aware, Universal Milan and our school, Shandong Ligon, we are going to have a collaboration in research and many other things. So he welcomes you to his want to receive your contact, so you can feel free to contact him. You can ask service computing, because he's the one of the most famous researcher in this area. Also, his colleagues, also his supervisor, is editor-in-chief of IEEE Transaction Journal. Yeah, we are going to build a good collaboration with Universal Milan. So, and he likes motivated students. So, yeah, I want you to keep studying hard. Also, again, thank you, Dr. Anisetti, for your valuable.
Thank you very much. Thank you,
Bye.
Professor. Thank you very much. Thank you for everyone. Thanks.